Let us consider a piece of paper. On one side, it is written that the statement on the opposite side is false. And on the opposite side, it says the statement written on the opposite side is true. Now, let's think this through. If the statement on the first side is true, then the statement on the other side must be false. But wait, that means the original statement on the first side is also false. Contradiction allowed. Let's try the opposite scenario. If the statement on the first side is false, then the statement on the other side must be true. But hold on, that means the original statement on the first side is true. Another contradiction. This type of paradoxes always highlights the challenges and intricacies that arise when a statement refers to itself, which can lead to logical inconsistencies and the boundaries of probability within formal systems. This might seem like a silly thought experiment, but in the early 20th century, it led Austrian logician Kurt Gödel were discovered that would change mathematics forever. He was the first one to show that the axiom of choice on the continuum hypothesis cannot be proven false through the accepted axiom of set theory and connecting classical logic, interstatistic logic, and modal logic.
Kurt Gödel was born the youngest of two on April 28, 1906 in Brann, Austria-Hungary, to Rudolf Gödel, a manager of a textile factory, and Marianne Gödel. Gödel suffered through several periods of poor health as a child. Gödel attended Evangelische Volksschule, a Lutheran school in Brann, from 1912 to 1916 and was enrolled in the Deutsche Stats Real Gymnasium from 1916 to 1924, excelling with honors in all his subjects, particularly in mathematics, languages, and religion. 5 years later, though he went to study in Austria at the University of Vienna, where he earned his doctorate in mathematics.
In 1928, Hilbert and William Ackermann published Principles of Mathematical Logic, an introduction to first-order logic, in which the problem of completeness was posed. Are the axioms of a formal system sufficient to derive every statement what is true in all models of the system? This problem became the topic that Gödel chose for his doctoral work. In 1929, at the age of 23, he completed his doctoral dissertation under Hans Horn's supervision. In it, he established his autonomous completeness theorem regarding the first-order predicate calculus. He was awarded his doctorate in 1930, and his thesis was published by Vienna Academy of Science.
In 1946, Gödel became a permanent member of Institute of Advanced Studies, where he came in contact of Albert Einstein. In 1951, he was awarded the first ever Einstein Award. In 1968, he was elected as a foreign member of Royal Society, London, and in 1974, he was awarded the National Medal of Science.
Gödel's discovery had to do with the limitations of mathematical proofs. A proof is a logical argument that demonstrates why a statement about numbers is true. The building blocks at these arguments are called axioms, which are some undeniable statements about two numbers involved. We don't need to prove these axioms. We assume them to be true without proving them.
Every system built on mathematics, from the basic number theory to most complex proofs, is constructed from those axiomatic pillars. That is, if a statement about numbers is true, mathematicians should be able to conclude it with the help of the axioms of that system. Since ancient Greece, scholars of mathematics used this systematic method to prove or disprove mathematical statements with total certainty, but some logical paradoxes, like the one mentioned at the beginning of this video, were threatening that certainty.
In the early 20th century, prominent mathematicians like David Hilbert, were eager to prove the consistency and certainty of the whole mathematical system. While it's relatively easy to create a self-referential paradox with words, numbers don't typically talk about themselves. A mathematical statement is simply true or false, but Gödel had an idea. First, he generated some code numbers representing mathematical statements or equations so that a complex mathematical entity could be expressed in a single number. This meant that mathematical statements written with these numbers were also expressing some characteristics about the encoded statements of mathematics. Thus, this method, named as Gödel encoding, allowed mathematics to talk about itself.
Okay, so now Gödel challenges us with the following statement. This statement cannot be proved from the axioms. So this is actually something that has a code number. We can talk about proof using numbers. So this will be a statement that can be changed into a mathematical equation. Now this means because it's an equation in mathematics, it's either true or false. So which is it? If it's false, that means the statement does have a proof. But if a mathematical statement has a proof, then it must be true. This contradiction means that Gödel's statement cannot be false, and therefore it must be true, that is, this statement cannot be proved. But it means we now have a true equation of mathematics that asserts it cannot be proved. This revelation is at the heart of Gödel's incompleteness theorem, which introduces an entirely new class of mathematical statement.
In Gödel's paradigm, statements still are either true or false, but statements can either be provable or unprovable within a given set of axioms. Furthermore, Gödel discovered that this type of unprovable true statements exist in every axiomatic system. This makes it impossible to create a perfectly complete and consistent system in mathematics, because there will always be true statements we cannot prove, even if one accounts for these unprovable statements by adding them as new axioms to an enlarged mathematical system. That very process introduces new unprovably true statements. No matter how many axioms we add, there always will be unprovable true statements in our system.
This revelation rocked the foundations of the field, crushing those who dreamed that every mathematical claim would one day be proven or disproven. Among Hilbert's 23 big unsolved problems, the second one was to prove that mathematics was in fact consistent. But what a shock he got actually 30 years later. While most mathematicians accepted this new reality, some fervently debated it. Others still tried to ignore the newly uncovered field. Still, Gödel's theorem opened so many doors rather than enclosing the old one. Knowledge of unprovably true statements inspired key innovations in early computers, and today many scholars of mathematics dedicate their careers to identify probably unprovable statements.
So while we have lost some certainty thanks to Gödel, so we can embrace the unknown at the heart of any quest for truth.
That's all for today, guys. Thank you for joining us on this captivating journey into the life and work of one of the greatest mathematicians in history. If you enjoyed this video, don't forget to share. Until next time, keep exploring, keep questioning, and stay curious.